Bismillahirrahmanirrahim. Assalamualaikum students. Welcome to Electronics. I am Madam Rosmina Zuin Abdul Rahim. So let's have a look on this one hadith. Safwan ibn Asar reported the Prophet ﷺ said, "No one leaves their house in search of knowledge, but that angels will lower their wings in approval of what he is doing." Source Sunan Ibn Majah. Okay, so being students of knowledge, you should always imagine that the moment that you come out of your house and go to classes, come out from mahala, go to classes, go to the labs, to the workshops, actually along the way there are many angels that are protecting you, many angels that are covering you, providing you shades and protection, lower their wings in approval of what you are doing as a student of knowledge. Okay, so by imagining so, you will appreciate yourself better as a student. Then obviously you know that you are always being protected by Allah Subhanahu wa Ta'ala. Okay, during this online class, although you are not leaving your house, but this concept also can be applied whenever you are having your online class. At the same time, angels actually are lowering their wings in order to acknowledge what you are doing. Now let's move on to chapter 2, still on semiconductor materials and diodes. Okay, in this chapter 2D, there are three subtopics, which are multiple diode circuits, diode AC analysis, and other types of diodes. Okay, for the first subtopic, which is the multiple diode circuits, what I need to mention to you, actually for multiple diode circuits, actually there is no specific technique that we can use to do the diode analysis, because the diode consists of multiple diode. Okay, it can be 2, 3 or more. Okay, but these are just the guidelines that you can follow. Okay, for you to do the analysis. Okay, first you may assume that all diodes to be on. Okay, when you assume all diodes to be on, at that time the diode can be represented with the three models. Okay, in this case it refers to model 2, where the diode voltage equals to V gamma. Okay, then you continue doing the analysis. Then maybe once you get all the parameters, you will notice that at that time maybe ID equal to 0 or ID equals to negative. Then you know your assumption is wrong, meaning not all diodes are on. Okay, in that case you know which diode should be off, so you need to somehow redo again with a new assumption and do the analysis. Okay, let's have a look on this example. Okay, it is called multiple diode circuits because we are having two diodes in one circuit. Okay, then first thing first, when you do the diode circuit analysis, obviously, as I always remind you, whatever incomplete connection, you have to complete the circuit first, so it will be easy for you to see where is the closed loop and everything. Okay, for example, in this case, this particular node is connected to 0 volt. What does it mean? It means that it is connected to ground. How about this one? We have negative 5, meaning this node is being connected to negative, while the positive one is grounded. Okay, then as you can see here, ground and ground at the same level, right? Okay, so you can connect them together. Okay, then for this negative 5, because the negative polarity is already represented here, so this value of this DC will be equal to 5 volt only. Okay, why 5? Because negative is already represented with this negative polarity. Okay, then have a look here at this particular node. It is connected to positive 5. What does it mean? It means that this particular node is connected to positive. Okay, and the negative one is grounded. Okay, so then this value becomes 5 volt. Same thing, ground and ground is at the same level. Okay, so now from here you can see actually you are having two closed loop, right? One loop here and another loop here, right? Okay, first let's assume both diodes are on. Okay, so we are having two diodes. Let's assume both diodes are on. So in this case, you can do KVL for the first loop. Okay, KVL for the first loop. So as you can see here, 5ID2, okay, plus 0.7, which is the V gamma across the D2, and plus 10 times ID2 plus ID1. Remember, the current flowing here should be the summation of ID2 and ID1, right? Then minus 5, okay, minus 5 considering this negative polarity, and minus 5 another one, okay, equals 0. This is KVL for the first loop here, okay. Then you are having two unknowns here, ID2 and ID1, okay. Then let's have a look for the second loop here, okay. You do KVL at second loop, and from here you can see 0.7, which is V gamma across D1, plus 10 times ID2 plus ID1, remember the summation of the current at this path, minus 5 equals 0, KVL at loop 2. So that's why you're getting this equation, okay. Then since you are having two equations together, you can equate them together, okay. Replace this term in the first equation just now. So in the end, actually you can solve for it, then find for ID2. In this case, it is 1 milliampere, okay. Then you check what is ID1, okay, because remember the question is asking for us to determine ID1, ID2 and V0, okay. So you already found for ID2, then let's check for ID1. Substitute in any equation, okay, because one unknown is already known, okay, which is ID2. So substitute accordingly. You are supposed to get ID1 value, but in this case, as you see here, ID1 is negative 0.57 milliampere. So negative current, it means that actually the diode is off, okay. What does it mean? It means that our assumption just now that both diodes are on is not accurate. So what you have to do, we need to calculate again, but now we know that the diode D1 is actually off. Why do we know it's off? Because as we can see here, ID1 is negative, okay. Okay, now we know diode D1 is off, okay, so you can simply replace it with open circuit here, okay. So obviously here there is no closed loop, okay, no closed loop, no current flowing, okay. So what you can do here, at this side you can still do KVL, remember, because we are still having the complete circuit here. Remember just now, just the same thing, we have 5 volt and we have another 5 volt here, okay. Okay, but now we already know that ID1 is actually equals to 0. Why 0? Because there is no current since D1 is off, okay. So you can do the same KVL equation, 5ID2, okay, 5ID2, okay, plus 0.7, okay, plus 10 ID2 minus 5 and minus 5 equals 0, okay. So in this case, there is only one unknown, which is ID2. You can simply solve for it. ID2 is 0.62 milliampere, and obviously ID1 is 0, okay. Then the next question just now is, what is V0 value? Okay, V0 value is the output voltage, okay. Then as you can see here, it is indicated in the circuit, V0 is at this particular node. What does it mean? It means that, let's say you imagine you go to the lab, you construct this circuit, then you have a multimeter with you. The multimeter has two probes, the positive one and the negative one, okay. So in this case, this is the point where we want to measure the output voltage V0, meaning you can put the probe, the first probe, the positive probe here at this particular node, because you want to measure the V0. Then the negative probe, where should it go? It should go to the ground. It should go to the ground, okay. So as you can see here, V0 is actually the voltage from this particular node to the ground, okay, to the ground. So here you can see that V0 is actually the voltage here plus the voltage here plus the voltage at this negative 5, okay. So if you see from here, okay, you can solve for this, where if you substitute accordingly, okay, because you already know the ID2 value, this is V gamma 0.7 plus ID2 times 5k here minus 5. So if you solve for this, you are supposed to get V0 value, which is 1.9 volt. Okay, here is another example, but I believe it's just the same like the one that we have discussed before. The only difference is now, just now this node is connected to 0 volt, remember? Now it is connected to 4 volt. Okay, so from here, what you can do first, remember you have to draw the complete circuit. Okay, so 4 volt meaning the positive one is connected to this particular node while the negative one is grounded. Okay, so we have 4 volt here, then we have negative 5 here, meaning the negative polarity is here while the positive one is grounded. Okay, this is 5 volt, ground, same level. The same goes to here, positive 5, meaning positive is connected at that particular node while the negative one is grounded. Okay, so you can see two closed loop here. Okay, first loop and the second loop. Okay, so just the same thing, you do KVL accordingly, because always start by assuming both diodes are on. Okay, so you do KVL similar like the previous example. For the first loop, you do KVL at the second loop, then equate them together. In the end, you are supposed to get ID2 is 0.2 milliampere. Then you substitute accordingly. In this case, you are getting ID1 0.63. So now you are getting ID2 positive value, ID1 positive value. So you know that your assumption is correct. Okay, so meaning both diodes are on. So from there, you can calculate for the V0 accordingly. Okay, because in this case, V0, remember, okay, is the voltage at this particular node, okay, with respect to the ground. Okay, one thing is you might see V0 as the voltage summation of voltage here plus the voltage here plus the voltage here equals to V0, right? Or you can see from the other side where V0, remember, at this particular node with respect to the ground, it can also be equal to the voltage here across R1 plus the voltage here, the 5 volt. Okay, so you can see from both sides. Okay, but it's just the same thing. Then if you calculate, you're supposed to get V0 equals 4 volt. Okay. Okay, here is another example. We have two diodes, so we are considering multiple diode circuits. In this case, you try to do on your own. Try to start with the first assumption, where the diode is on first. The diodes are on. Now, then check what are the currents that you are getting. Okay, then the final answers are given. Okay, so do this for your self-revision. Okay, now we come to the second subtopic, which is on this diode AC analysis. Okay, so in this diode circuit, okay, we are going to deal with AC signal, but before that, we need to recall the signal representation. Okay, where a signal actually consists of DC component and AC component, remember? Okay, so the same thing goes to the diode AC analysis, because in one circuit there will be the DC component as well as AC component. Okay, for this diode circuit, as you can see here, there are both components of AC as well as the DC, meaning to say the current and voltage associated to the diode actually contain both components, the DC component as well as the AC components. Okay, so the same thing goes to the voltage, DC component and as well as the AC. Okay, so in terms of graph representation, as you can see from here, okay, we have the DC ID and as well as the AC ID, and DC voltage as well as the AC voltage. Okay, this slide actually shows you how do we do the derivation in order for us to represent the diode in AC analysis. Okay, because as we know, in DC analysis, diode can be represented with the three model. Remember, the ideal diode, the one with the V gamma, the one with V gamma and RF. Okay, that one is for DC analysis. But how do we represent the diode in AC? Okay, it is based on this derivation, but I want you to go through the slide. Okay, it's straightforward. Then you will know how do you get the value, how do we represent the diode in AC. So if we continue the derivation just now, at the end, what I want to highlight here, where in the end, RD is given by VT over IDQ. RD actually is the resistor across the diode, meaning whenever the diode is on in AC analysis, it can be replaced with a resistor value. RD, what's the value of RD? Equals to VT over IDQ. VT is the thermal voltage, IDQ is the diode current in DC. Okay, so VT is thermal voltage, remember 0.026. Okay, then IDQ is actually the DC current. Okay, meaning to say, in order for us to find for the in order for us to do the AC analysis, we have to do the DC analysis first. Why? Because we want to find for the DC current, then only we can represent the resistor RD accordingly. So basically for the diode AC analysis, okay, so if you can see from this circuit, actually for the diode, it is being connected to both signals, right? VI is the AC and VPS is the DC. So in order for us to do the analysis, actually we can do the DC analysis first, then later we do the AC analysis. And in this case, we can apply the superposition theorem, remember? Okay, first we turn off, whenever we want to do the DC analysis, first we turn off the VI. Okay, we turn off VI, make it short circuit. So in this case, we are considering only VPS when we do the DC analysis. Okay, then the diode can be replaced with the three modules, remember? It can be equal to short circuit for either diode. In this case, it is in for model 2 equals to V gamma, or it can be V gamma and having RF in series, remember, for the third model. Okay, so you can represent the diode accordingly and find for the ID as well as the VD. Okay, but when we are considering AC analysis, this time VPS will be turned off. Okay, so as you can see here, VPS is being short circuit. We turn off VPS because it's DC component. Now we are considering AC analysis. So the diode is connected to VI, but in this case, for AC analysis, the diode is replaced with RD, a resistor with a value of RD. Remember just now from the derivation, RD is given by VT over IDQ. VT is the thermal voltage 0.026 volt, and IDQ actually you are getting from the DC component, DC analysis. Meaning to say, we have to do the DC analysis first and only we can do the AC analysis. Okay, here is one example, okay, on how do we do the DC analysis for the diode circuit. Okay, so all the parameters, the circuit and diode parameters are given. Okay, so as you can see from this example, we have VPS 10 volt, R value is given, V gamma is given, VI is given. So as you can see here, V gamma is given as 0.6 volt, meaning in DC analysis, we have to consider the second model. Okay, so what should we do first? Let's say we have this original circuit. Since we are now considering the DC analysis first, so what happened to VI? VI we replace with short circuit. Now we are only considering VPS, okay, because DC analysis. And for the diode, we replace it with V gamma. Okay, then you just do the same like the previous analysis. In this case, let's say you want to find for the ID, we can do KVL, right? Minus VPS plus V gamma plus IDR equals 0. Okay, so from here we can find ID, which is actually VPS minus V gamma over R. Okay, so if you substitute accordingly, you are supposed to get the ID value 1.88 milliampere. Then the question is asking for output voltage of the DC component. Okay, so V naught simply, since you already found for ID, R is given, so obviously V naught is the voltage across the R, right? So V equals IR. Straightforward, you can find for the V naught for the DC analysis. Okay, so you are getting ID and you are getting V naught in this case. For the same circuit, now let's do the AC analysis. So as you can see here, VPS you replace with short circuit. Then we have VI here for AC analysis. Then remember the diode is replaced with resistor RD. and in this case RD equals to VT over IDQ. VT is the thermal voltage, IDQ is the diode current coming from the DC component just now. Okay, so you substitute, you are supposed to get the RD value. Then the rest you just do accordingly, since we want to find for the ID. So same thing, we do KVL. Okay, minus VI plus IDRD plus IDR equals 0. So in this case, you can find for ID, which is given by VI over RD plus R. Okay, so you get this equation, substitute everything, you are supposed to get the ID. This ID is the AC component. Okay, then in this case, you are supposed to get the V0, the AC component of the output voltage. V0 equals to IDR. Okay, just the same thing, but in this case, obviously it is in the form of sine omega t, because we are talking about AC signal. Okay, so just to recap the diode AC analysis, first we have to do the DC analysis first. Okay, then consider the three models, then we calculate the ID. From there only we can calculate for RD value to represent our diode in AC analysis. Then only we can do AC analysis using the resistor RD to find whatever parameters that we are supposed to find in AC circuit. Okay, here is another example of diode AC analysis where we are having both VI and VPS. VI and VPS, all the values are given. Okay, in this case, I reserve this example for you for your own self-revision. Try to do on your own using the same example, the previous example that I have shown you. The final answers are given here. Okay, you just check your answers later. Okay, for this example, the circuit schematic looks a little bit different, but it's actually just the same, where the diode circuit contains both AC and DC. So as you know, we start with the DC analysis first, okay, as shown in circuit A here, and then only we continue with AC analysis. In this case, you have to determine the diode voltage when V gamma is given as 0.7 volt, meaning to say we know that during DC analysis we have to consider for the second model. Okay, so that's why in DC analysis this diode can be represented with V gamma of 0.7 volt. Okay, then later once you find for the current and the voltage, you can simply represent the diode with RD value in AC analysis, remember, to find the same current and the diode voltage. Okay, now we come to the third subtopic, which is the other types of diodes. Okay, there are 5 diodes that we have to know. The first one is the photodiode. Okay, where photodiode is actually a diode that converts the optical energy into electrical energy. Okay, so when it is being exposed to the light, it will somehow convert the energy to the electrical. Then we have the second type, which is the solar cell. The concept is just the same like the photodiode. Okay, but this solar cell is actually used more to supplying power in electronic circuit. Okay, then the third type is light emitting diode, LED, and it's actually the opposite to the photodiode, where in LED it converts electrical energy to the light energy. Okay, a good example of LED together with the photodiode we can show from this figure. Okay, we can see from this figure where we have the transmitter and the receiver. Okay, the signal transmission. So at the transmitter side, the electrical energy is being converted to the light energy through the LED. Okay, then this light energy will travel through optical fiber, which is connected to our house. Okay, then at the receiver side, this light energy is converted back to the electrical energy for us to power up the electronic system. Okay, so it's a good example for both LED and photodiode. Then for the fourth type, it is a Schottky barrier diode. For the Schottky, important thing that you have to know is the turn-on voltage for Schottky is much smaller compared to the normal PN junction diode. So as we can see from here, for normal PN junction diode, maybe V gamma equals to 0.6 or 0.7 volt, but for Schottky barrier diode, it is much lower, which is actually an advantage because we just need to supply small voltage to turn on the diode. Okay, actually the fifth diode that we need to consider is called Zener diode. Okay, but before that we need to understand one concept which is related to Zener diode. It is called breakdown voltage. Okay, so if you can recall, when we have the IV characteristic of diode, ID versus VD, at the forward bias side, remember you have this curve, okay, where initially there is no current, but after V gamma there will be current, right? Okay, then we are saying all this while that at reverse bias there won't be any current. Okay, why? Because remember the depletion region becomes wider, right, at PN junction, where we connect it to reverse bias, positive to negative and the negative type to positive. Okay, the depletion region becomes wider because of increase of electric field, remember? Okay, then at that time we are saying no current, but actually if we keep increasing the voltage, there will be current. Okay, there will be current. Okay, then this phenomena is called as breakdown voltage. Okay, then why suddenly there will be current? Because when we keep increasing the voltage, the reverse bias voltage, actually in the end we are increasing the electric field, remember? Okay, then when electric field becomes so big, okay, we come to a stage where suddenly it will cause the covalent bond to break. Okay, once covalent bond is being broken, it will cause electron hole pairs to be created. Okay, so obviously you know, once there will be free electrons and holes, obviously there will be current. Okay, so this movement because of the reverse bias current is called as Zener effect, and it occurs at breakdown voltage. Okay, so we have a very special diode, okay, to tolerate the breakdown voltage, which is called as Zener diode. Okay, why it can tolerate the breakdown voltage? Because it is highly doped. So if you know it is highly doped, meaning it has very high impurities. Okay, so as you know, impurities will cause increase of carriers, increase of holes, increase of free electrons, right? So obviously there will cause increase of current. Okay, so Zener diode is very special because it can tolerate the breakdown voltage, and this is the symbol of Zener diode. Okay, so it's similar to PN junction diode, but it's a little bit different, right? Okay, then the interesting part of Zener diode is when it is reverse bias, it can the current can flow, okay, because it can act under breakdown region, okay, the one that we discussed just now. But when it is forward bias, it still can flow the current, but at this time it acts like normal PN junction diode, meaning to say it can work in both directions. Okay, another interesting concept that we have to know is called as avalanche effect. Okay, avalanche effect is actually similar to the breakdown voltage just now. Okay, where when these carriers actually crossing the depletion region, the space charge region, they also gain enough kinetic energy, meaning they are so very energetic. Okay, where does this energy comes from? Obviously from the electric field just now, because we are supplying the negative voltage to the PN junction diode, right? So what will happen, if you see from here, electron with high kinetic energy will collide with other atoms. Okay, so as you can see, it will cause many other free electrons and holes to be there inside the structure here, inside the atomic structure. So obviously this will contribute to more collision in the future, then obviously more and more free electrons and holes, which will contribute to the current. So as can be seen here, okay, Zener diode occurs at low voltage, okay, as compared to the avalanche effect, which occurs at much higher voltage. Okay, so this Zener diode, I mean, can tolerate this Zener effect at low voltage because of it is being highly doped. Okay, then for normal PN junction diode, still can get the same breakdown effect, but it goes through the avalanche effect, and by then actually this normal PN junction diode is already damaged. Okay, so we have a special diode to deal with the breakdown, which is called the Zener diode. Okay, this table shows the comparison between PN junction diode and Zener diode, but everything has been discussed in previous slide. Okay, this is one example of Zener diode circuit. Okay, but I think I want to discuss this later in chapter 3, Zener diode analysis. So that's all about chapter 2D, where we have 3 subtopics: multiple diode circuit, diode AC analysis, and other types of diodes. Okay, with that, thank you so much. Bye.